So this section is all about how can we measure, how can we conduct investigations and experiments to actually be able to calculate the speed of waves in different media actually. So for example, the speed of waves in water, we could be expected to calculate the speed of waves in the air, so in a gas, and also in solids such as a metal rod, which is what we do for the core practical in this chapter. I'm going to start, before we actually look at the equations that can be used, we can look at this example. So how would we find the speed of waves in water, for example, in this specific situation? Now, we already have an equation from SP1, which was speed equals distance divided by time. Now, there's no reason you can't apply that same equation, even though it was used to find the speed of an object moving or someone running. You can still apply that same equation to waves as well. So speed equals distance over time is our first equation that we're going to use. But in terms of what we need to measure, to be able to calculate the speed, we need a distance and we need a time. So in this example, the distance that we're going to use is between these two sets of ladders. Now, in an exam, you'd say find the distance between 2 points, point 1 and point 2. But you'd have to say with what measuring equipment are you actually using in order to determine that the distance between these two ladders is 10 meters. So what we're going to suggest, obviously generally you could use a meter rule to determine the distance, you could use a tape measure to measure longer distances, or for things like this, such as a 10 meter distance, you might want to use the trundle wheel, which is the circular wheel that every single time that wheel turns, it has a circumference of 1 meter, it clicks and tells you when you've passed 1 meter. So for this one, I'm going to suggest to measure the distance between 2 points, we use a trundle wheel. We're saying that it's going to be 10 meters for this example. What I need to do is, you can see the water waves here. We know from 4a that these water waves are transverse, and the water here is not travelling along, it's just moving up and down, perpendicular to the wave. So what we want to do, but the wave itself will move, so it looks like the wave and the water is moving, but really just the energy of the wave is moving, but the water is just oscillating perpendicular. We want to follow one wave, so we want to know what time is it going to take for one wave to pass between this ladder and this ladder. And we're going to do that using a stopwatch. So we're going to time one wave from point number 1 on the first ladder. How long does it take for it to travel across and past the second ladder is where we'll stop our clock. So we have a distance of 10 meters and we have a time from the stopwatch for one wave to pass between the 2 points. Speed equals distance divided by time, and it will tell me the speed of those waves. One thing to make sure that you note, in this method of distance and time, distance was quite accurately measured. The trundle wheel will give me a very nice accurate measurement for the distance. However, using a stopwatch to measure the time for just one wave to pass can be quite difficult, and it can make the value for t quite inaccurate. The problem is, these water waves might be travelling very fast. Now, if you need to get a stopwatch with human reaction time, which isn't the fastest reaction time, see one wave when it passes the ladder, and then it could be travelling very fast between the two, and then stop the clock when it passes the next. It may be very, very difficult to do that with just one wave if they're travelling really fast. Okay, so that value of time might not be the most accurate value, and therefore the calculation of speed may not be the most accurate calculation. There is an alternative method for calculating the speed of waves, and therefore we're going to use and introduce a new equation. So this equation, wave speed equals the frequency of the wave multiplied by the wavelength. If we were to write that in symbols, it would be v for velocity of the wave equals f times lambda, which is a Greek symbol, or the Greek symbol L in the Greek alphabet. So v equals f lambda is the equation for calculating wave speeds, the second equation that we can use. Now, if we go back to this situation, we now have a new equation which is v equals f lambda. Wave speed equals frequency times wavelength. The frequency, by definition from 4a, was the number of waves passing a point every second. Now, if I pick just one point, I'm going to pick this ladder on the left. That's my point. And what I need to do is I need to count how many of these water waves are passing this ladder every second. But again, 1 second is a very short period of time. If I have to do that with a stopwatch, I have to go stop, stop in 1 second and try and count how many pass. It's going to be very difficult for me to do that. It's going to be very inaccurate. So what I can do is actually increase the amount of time that I measure the number of waves passing this ladder So I could say, let's do it in 20 seconds. Make it easier for me to measure with a stopwatch, make my value for frequency more accurate. I would count how many waves pass this point in 20 seconds. So I start my clock. I count 1 wave, 2 waves, 3 waves, and I stop my clock at 20 seconds. Let's say I got 10 waves past this point in 20 seconds. If I want the frequency, which is the number of waves in 1 second, I divide by 20 seconds. So 10 waves in 20 seconds is 10 waves divided by 20, which is 0.5 hertz. So the frequency would be 0.5 hertz, and that is a more accurate value than measuring just the time of one wave or in 1 second for the frequency. So I have quite an accurate value of frequency. In order to find the wavelength between 2 points, what you need to do is choose your 2 points again. So we go back to our 10-meter distance between the 2 ladders. And what we do is, because these waves, although the waves are traveling across, the water waves remain the same because the water just moves up and down. So you should see this same image the whole time. If you took a still image of that, you would see exactly what is here, which is 1, 2, 3, 4, 5 waves in that 10-meter distance. 5 waves between 2 points. So I count or measure the distance between 2 points. I count the number of complete waves between those 2 points. And all I need to do to find the wavelength of just one of those waves, I do 10 meters divided by 5 waves to find the length of one. And obviously 10 divided into 5 parts is 2 meters per wave. So the wavelength of these waves is 2 meters. We said the frequency, for example, was 0.5 hertz. All I need to do, frequency multiplied by the wavelength, and I find the speed of the waves. So that's how we can calculate the speed of waves. We either use the distance divided by time, or we use frequency times wavelength. And in terms of measuring the distance and measuring the time, there are different examples in water. There are obviously different examples in air. So to give you one example of how to measure the speed of sound in air, one very simple one would be to create a sound a certain distance away from a wall. You make a sound, the sound travels to the wall, and then it travels back as an echo, and you receive the sound. So you make a sound, you start your stopwatch, it travels, it comes back, and when you hear the echo, you stop the watch. So there's your time. Now the distance travels, you need to measure from you to the wall and the wall back. The total distance is to the wall and back. So your distance would be there and back. Your time would be the time taken to create the sound, and then the echo to come back and receive the sound. The further away you are, the more accurate this will be, because of course sound travels around 330 meters per second in air. If you're not, basically, if you were 330 meters away, or half of that for it to go and come back, it would literally take just 1 second to go and come back. That's quite a short time. So what you want to do is increase the distance between you and the wall, so when you make the sound, it travels far enough that there's a significant amount of time for you to measure on your stopwatch. It comes back, you measure the time you receive the echo, and you do distance, total distance, divided by time. That's one way. Another way that comes up in the CGP booklet, revision guide as well, is quite a little bit more complicated, is what you do is you use 2 speakers, a microphone and a speaker, one which is creating sound and one which is receiving sound. And what you would do then is you would connect these microphones to what's called an oscilloscope. So an oscilloscope is a device, an electrical device, where if you plug in, it receives a sound signal, it turns the sound into an electrical signal, and it creates a curve on the screen which looks a little bit like a transverse wave, but it's just an electrical signal that's been converted from a longitudinal sound wave to an electrical transverse wave. Now what we need to do, with 2 microphones in the same position, the sound waves will be exactly the same on the screen. So you'd have wave number 1 and wave number 2 exactly the same underneath. What happens is, if I move one microphone further apart, those 2 waves are going to shift. So they'll be exactly the same when the microphones are at the same position, creating and emitting sound at the same point. But as soon as I start to move one of my microphones away, it will receive sound a little bit later. So the sound is coming from the speaker, my microphones are measuring the sound, and then as I move one away, it takes longer for the sound to get there. So the 2 waves on the graph, they start to look different and no longer match. So they start to change. Now if I move the microphones away to the perfect position, just far enough that the 2 waves that change come back to being the same, then I must have moved one complete wavelength. Because if the waves match, and then they move, and then they match again, one whole wavelength has been moved. If I move the speakers, let's say I move the speakers 2 meters, I moved the speakers 2 meters in distance before the waves came back together, then one wavelength must be 2 meters. So the wavelength can be found by the distance between the 2 microphones when the 2 waves on the oscilloscope go back to being the same wave. Alright? So that's how I find my wavelength. The frequency comes from the sound. I can use a speaker, I can connect it to a frequency generator, and I choose the frequency myself. So I have the frequency, and I know that the wavelength is the distance between the 2 microphones when the waves match up again. So I just multiply the 2, and I find the speed of sound in air that way as well. Okay, so that's 2 methods for measuring sound in air. We obviously, in the core practical, we're going to look at how to measure the speed of sound on the ripple tank, and also how to find the speed of sound in a metal rod as well. Okay, but that's it. There are 2 equations for speed, distance over time, and frequency times wavelength.